Good morning, ladies and gentlemen. Excellent, excellent. I hope you had a great day yesterday. Saw a lot of enthusiastic networking going on, some great panels, very informative, and we're going to continue on with that here today. So we're going to begin today with our plenary speaker, and it's my great pleasure to introduce our featured speaker, Mr. Ben Byboth. Ben leads commercial strategy and business development at Commonwealth Fusion Systems. Before joining CFS, Ben held leadership roles at Eversource, Entergy, and NextEra, where he launched new energy businesses, led modernization of the grid, and developed new and innovative regulatory strategies. He's a great U.S. Navy veteran and a former nuclear plant operator. His career spans legacy nuclear fission, renewables, storage, grid modernization, and now fusion energy. At CFS, Ben engages potential fusion customers, partners, and stakeholders, educating them about fusion's clean, abundant, zero carbon advantages, how to overcome barriers to its adoption, and supporting siting and development for ARC, the world's first grid-scale fusion power plant. He holds an MBA from Tulane University and a Bachelor of Science in Nuclear Engineering Technologies. Ladies and gentlemen, please join me in welcoming Mr. Ben Byboth.
Good morning, everyone. I'm very happy to be here today to talk to you about fusion, something I'm extremely passionate about, extremely excited about today. So thank you all for being here. Thank you for the mission that you're on and what you're doing here in service to this beautiful state. As I've driven around and learned more about Virginia, you're really spoiled with natural resources, and so the preservation of those is really, really important. So thank you for your work. We're going to talk about fusion today. I'm going to talk for about 30 minutes, then we'll have some time for questions. My intent is to really cover about three things. I want you to introduce you to what fusion is and why we're excited about it. I also want you to get a little bit of orientation of who we are at CFS and what we're doing to help accelerate the urgent transition to fusion energy. And then we'll talk about where we're going and about what we're doing and coming into Virginia to do here with fusion. And then I'll show you some pictures of our progress to just give you some scale of the progress that we're making at our campus up in Massachusetts. So what is fusion? Fundamentally, it's a reaction, and it's the most common reaction in the universe. It's the universe's unanimous choice as the source of energy. Over 99.99% of all energy comes from fusion in the form of what happens in the stars, where hot plasmas are confined by gravity to make and fuse particles together to make energy, and in the process releasing enough energy to power our solar systems and our lives today as we know it. And so it is fundamentally the opposite process of fission, where fission, with my background I did for a long time, is taking big heavy particles and breaking them apart, releasing energy. Fusion, again, combines the most abundant and lightest isotopes together to make heavier ones, and in the process releases about 4 times more energy than you would from a fission reaction, and about several hundred million times more than you get from just burning something. And so what we do and what we try to do with fusion is we have to build a machine that can fundamentally recreate the conditions that we have in the stars here on Earth. And that, I think when you look at what fusion is, there's a lot of things that people are really excited about. I think fundamentally, the first thing is that it's clean. I talk about taking hydrogen together to make helium. That's the byproduct. We don't make a lot of it. We use very little amount of fuel to make this happen. But helium's the only real byproduct of the reaction. We talk about it being safe. I'll talk about this just a little bit more in a few minutes. But it is fundamentally an inherently safe process. It is not subject to runaways or meltdowns that you have traditionally with legacy nuclear projects. We talk about it being on demand. That means that it's available, that you can ramp it up, you can ramp it down, you can respond, you can integrate it with renewables and make it a good foundational piece that can allow for the best benefits of renewables, but also allow for a base load stable project that can support the growth of the grid. And then we think about this being able to deploy around the world and be a very scalable resource. And with that comes a measure of energy sovereignty, because basically if you have water, you can have fusion once you have the machine. It is a real fundamental shift from the way we think about energy today, which is the hunting and gathering of resources, the scavenging of things, the moving and digging up of things and moving them, burning them, or collecting them intermittently. It is moving away from those to really energy as a technology and breaking the tether from these other resources. Where again, like if you had a bottle of water, just a regular bottle of water, that's enough energy or fuel inside that bottle of water for your entire lifetime. And so it's a very, very big difference in how we think about it. It is moving to a technology where if you have a machine, then you can push a button and get heat from. It is changing the paradigm of energy as a technology, not as a resource or resource consumption. So I mentioned the safety. Just want to reiterate here again. The fusion process, because we're talking about working with a plasma that we're confining, and I'll talk a little bit more about how the machine works as we go through this, fundamentally that any introduction of air into the system immediately stops it. It takes a lot of work to cultivate the environment, to keep a little bit of a star comfortable in a bottle, and that anything that stops that will stop it immediately, and will cause that to all things stop. There's also, we don't use any special nuclear materials, we don't use the uraniums or plutoniums, and so there's really no of that long-lived nuclear waste that comes from those decay chains. There's no significant health or safety impacts to the local environment around us. So it's a lot of the benefits that we've always talked about with fission before, but really made much, much better through fusion as a much more safer and sustainable place. Okay, so this is awesome. You may have heard, I hear it all the time, fusion's 30 years away, always will be. It is, that belies a lot of progress that has been made. And so over the past several decades, we have been making progress at a pace that's about the same or faster than Moore's Law on how we improve on a key metric. And one of the great things about fusion is that we've actually been doing fusion here on Earth for a long time. We've been doing it since the 1950s. And we've been making progress towards a goal where the fusion reaction actually produces more energy than it takes to run the reaction. And at that point, that ratio is called Q. And what you want to have on this graph is this Q equal to 1. If you're below this graph, you're a really cool science experiment, but you're not a power plant. If you're above this line, then you're making more power out than in, then you can start to harvest that and start to use it for other things. So that's been the goal. And so there's been a bunch of machines that have been built over time. And we understand these machines and their characteristics, and this graph is actually, which you can understand a little more, this is temperature down here on the bottom. So when we talk about wanting to make fusion happen, we do it in plasmas that we get very, very hot. Because in a plasma, the electrons come off and you've got this soup of charged particles, and you want those charged particles now, the nucleus, to get together. And so you have to accelerate them and get them going really, really fast. And so they overcome that natural push. You have to have them moving fast. That speed is equates to temperature. And so down here on the bottom is temperature. And the other two terms over here are density and confinement time. So how dense is your fuel and how long can you hold it in place? Those are all about probability. So if you have enough energy in your fuel and you then can improve the density and confinement time, then you know how it's going to go. This also allows us to project how future machines will perform with relative certainty. And so what CFS is building now is a machine called Spark that will not only get Q greater than 1, it'll have Q greater than 10. And so this will be a big change and breakthrough in where it's going. And so fusion is much, much closer than people have thought. And I'll continue to explain that as we go through. So just a little bit about CFS now. I've told you a little bit about fusion. Let's talk a little bit about Commonwealth Fusion Systems. Commonwealth Fusion Systems was spun out of the MIT's Plasma Science and Fusion Center, which was a leading research institution for plasma science. And this machine here was called the Alcator CMOD project. It was a fusion machine that was in Cambridge, Massachusetts, right in the middle of near the MIT campus. It set records for plasma temperatures and pressures. This is where our CEO, our chief science officer, and several other members of our team got their PhDs while working on plasma physics and working on an actual fusion machine. We then at CFS have innovated on a new class of magnet, a new type of magnet. So you're making a magnetic bottle, and you want to make that as strong of a magnet as possible because it actually works that it scales to the 4th power, where if you can double the magnetic field, you can get 16 times the performance of your machine. And so that's what CFS has really been put together to do. is expand and build upon a magnet technology. And we did that and demonstrated that to the world in September of 2021. And then now we're building a machine called Spark. Spark will take this same known architecture before that we used with the Alcator project, add this new class of magnets and bring that all together in one package. And then Spark will be the first machine to continuously, in a commercially relevant architecture, demonstrate net energy gain from fusion. And then from there, we'll be moving to ARC, which will be the project that we've announced that we'll be building in Chesterfield County, just south of Richmond, Virginia. A little bit more about CFS. It's a really incredible place to work. I'm honored and humbled all the time by the people I get to work with. We're now have grown to well over 1,000 employees. We've raised more than $2 billion in private capital, predominantly all private capital, very little amount of government support so far. But working to advance this with a large cross-section of people from technologies. We build our company off of people who have a big academic background, who have done research and are on the cutting edge of the science, because fusion is at the edge of the science in almost every direction you look. And we brought together people who have done a lot of work building big things, be it submarines or whatever. And we've also brought people that have built things really fast, like SpaceX. A lot of employees from the SpaceX team have come over to CFS. And so that team is getting together. One of the things we like to say is that we are building upon this known platform. This device and architecture is called a tokamak. It's been around since the 1950s. There's been over 200 of these built. The physics is very well understood. And so what really we are into now is an engineering and integration challenge to take a new class of magnets and put them together into the machine to make that work. And I mentioned those magnets. So we use a new class of materials called a high temperature superconductor. This is not room temperature superconductors, but this is a new material, relatively new, discovered in 1986, won the Nobel Prize. This, if you could tell from previous superconductors that we've had around for a while, they're in MRIs, they're been used in other fusion machines. These low temperature superconductors have a limit in how strong of a magnetic field you could build. And so before that, you made magnets out of copper. Copper works for really strong magnets, but it gets really hot. Low temperature superconductors allowed you to have continuous without overheating, but the magnetic field was limited. So the new superconductors are really the breakthrough that enables you to actually now create that stronger magnetic field. What that means is that you can shrink the size of the machines. And so this is a big research project in the south of France called ITER. It's a big multinational project to try to show the world that fusion can work. It was built out of low temperature superconductors. Both these machines will create a Q of 10 roughly. But this machine obviously being much, much bigger, there's a person right there for scale. And then that's the machine we're building in Massachusetts. So about 1/40th the size. And it's the real power that the magnets create for and leverage for the fusion machines. So I mentioned Spark. Spark is our first demonstration pilot machine. It is will be the world's first machine to continuously make Q greater than 1. It will demonstrate actually more than 10 times power out than in. It's not a power plant, but it will make about 100 megawatts of heat. We know how to take heat and turn heat into power through steam. We've been doing that for well over 120 years. So this will really be a risk retirement platform that shows the ability to continuously make a lot of heat. As you can see, this is quite far along. This is now into commissioning phases of a lot of the systems and moving forward on a lot of installation. Something about CFS is we're very committed to peer review. And so we're often looking for and trying to build transparency and trust in the work we're doing. And so we've published a lot of papers, now well over 60 papers. But we also published, when we first laid out our plan, 7 papers in Journal of Plasma Physics. And so we've got peer-reviewed papers that this machine will work and perform as we've designed it to once we get it built. And so there's a lot of excitement around that this machine will, in fact, work. And it paves the way as a risk retirement strategy towards our commercial project we call ARC. ARC will be about twice the size physically of the device, but still at that size, roughly, this machine here is about the same size as an offshore wind turbine nacelle. So still a very compact machine in size overall. ARC will be about 400 megawatts of electric power that can go to the grid. We'll put it onto the wholesale grid and sell electricity. We can ramp it up or ramp it down. It makes a lot of heat, so process heat in the order of about 600 degrees. Our first market's going to be primarily focused on electricity production, but there is a lot of opportunity for cogeneration or decarbonization of a lot of industry with that type of heat. Relatively small footprint. This is the actual rendering of what the device will look like. tend to make it look more like a big box store than maybe what you think of from a power plant. But this is the rendering for the facility that we're going to be building in Virginia. And then this is the site where it's going to go in Virginia. And so we are really excited, obviously, to be coming to Virginia. Part of coming here is really getting an opportunity to take advantage of a really strong workforce at the nexus of really the energy transition, where you've got the highest load growth in the country, and you've got this great opportunity to be a part of that solution as part of bringing more affordable, more reliable, and then ever cleaner power to the Virginia grid. It's a big part of the excitement. And then our partnership with Dominion is a great opportunity for us to teach and learn simultaneously. We'll teach Dominion a lot about fusion, and they'll teach us a lot about how they interconnect to the grid, which will be really helpful for us as we go forward and kind of bring those two strengths together as companies. It's a compact footprint, so that 400 megawatts will be roughly the same size as a 400 megawatt natural gas plant. So not a very big structure. We're looking at probably 25 to 30 acres in the future is what we'll need to be able to build one of these. So tight in space, and which is helpful. So let's talk a little bit about how it's actually going to work, just so you can kind of get a picture from what this does. So this is a device we call a tokamak, as again a Russian word because the Russians built the first one in 1958. It stands for a torus or donut shape right here that is then confined by magnets around the outside. So the torus confined by magnets. Inside the device, we add a little bit of fuel, just a few grams. In fact, when this machine is operating right now, there are more particles in my lungs as I speak to you than there will be inside this machine as fuel. So literally grams of matter inside. And so we'll add that little bit into a vacuum vessel. So we'll pump down the vacuum vessel, and then we'll add a little bit of fuel. And then we'll turn on some big magnets, starting with this big central solenoid in the middle, this number 4 here, and these big outside magnets around the outside. And those magnets will then drive that and heat up that plasma and start to turn it, or heat up that fuel until it turns into a plasma. And then we'll add radio waves from the side here, basically 122 megahertz radio signal just broadcast into the plasma to heat it up and get it even hotter. And then from there, the fusion reaction will start to happen. And once you get the fusion reaction happening, we take 2 isotopes of hydrogen, one called deuterium, which naturally occurs in all seawater, tritium, which is a little bit rare. It's like in the upper atmosphere. We'll talk a little bit more about tritium. But we fuse those 2 together, and in the process, we make helium, and we have 1 extra neutron. That neutron is the energy carrier, which will carry the energy from the plasma out into a big molten salt tank, this number 7 area. And that molten salt will then get hot, and we'll pump that molten salt over to a heat exchanger. And so from the machine itself, that molten salt will get hot. It'll go to 1 heat exchanging loop, and then to another heat exchanging loop, and then we'll make steam at this point, and then that steam will then go to turn a turbine, roundy, make lots of electrons. As we go forward, looking down from the machine, just to give you an orientation of what a fusion plant actually looks like. So you've got in the middle is the tokamak, and then everything around it is something that's either coming in or going out. On this side, you've got the heat coming out in the form of the molten salt heat exchangers to the other set of heat exchangers, and then to a steam turbine over on the side. And then in the back, we've got a cryogenics plant. So I said they're high temperature superconductors. That's a relative term. We still cool them down quite a bit. And so we use a cryogenics plant to keep those magnets cold, because the colder you get them, the more current they can flow. The more current you can flow through a magnet, the stronger the magnetic field. We also have over here energy storage devices. So this machine will fundamentally work as somewhat of a pulsed machine, and then we'll have to store energy for that. So going back to this picture, when the machine is running, this big central solenoid here in the middle actually acts on the plasma to drive it around and drive the flow of the plasma inside the machine. And so that central solenoid here will need to be reset about every 45 minutes for a few seconds, and then starts up again. And so that constant process is the way we keep making it work. But that takes a little bit of an energy draw, so we put batteries on there that will charge up during that period. And then the other side is, this is a nitrogen plant. So we use nitrogen to pre-cool the systems. So liquid nitrogen is part of our cooling system. Just make nitrogen, take it out of the air, and then compress it, make it into a liquid. And then you can cool everything off. And then on this side, one of the big pieces that we have to do for maintenance is this vacuum vessel is designed to be replaceable over a period of time. And so we'll have to replace that probably somewhere between a year and 2 years of operations. And so this is representing the storage of those materials and the where we can put those in and take them out of the machine. And in the front's a bunch of diagnostics and support systems. So that's a fusion plant. So it's going to be some updates on progress and where we're doing real quickly on pictures. So Spark is moving together really fast. This is some pictures of the machine itself. We're now more than 50% complete. As I mentioned, some of the systems are now in commissioning mode, and we're turning on systems for the first time. We have fluids and systems. Things are happening. There's a look at the machine from the front overhead. This is a look at the cryo plant. These are big compressors that we use to compress helium that we use to cool the magnets down with. This is looking up from the bottom of the machine. You can see a lot of infrastructure moving around. I'll point out real quickly that for this machine, that line right there is the fuel line. So that will make 100 megawatts of heat on a line that's about the size of a pinky here. Looking up from the bottom, that's about all the basement you have. It's really relatively compact. Some of the electronics we need to run the radio frequency signals to produce that 122 megahertz signal that heats the plasma. So look at the vacuum vessel. The inside there will have a plasma whose temperature will be in excess of 150 million degrees when it's operating, but very, very low density. And then some look at the hardware. So this is one of our big magnet cases. This is when the magnet's put together, it's about 30 tons, has about 100,000 pounds of force on it. That whole case will stretch about 1.5 inches because the magnets are so strong when it's operating. And this look inside the tokamak hull. That's a picture on the wall. That's not the actual machine yet, but the stands and stuff are getting in place, getting ready to receive that vacuum vessel and the magnets that are coming off our manufacturing facility. Our magnet factory is up in Massachusetts, so we're vertically integrated to the production of our magnets. We make all those in-house. So we have a 100,000 square foot manufacturing facility. Here you can see technicians adding. That's the superconducting tape. This is what the superconductor looks like. One strand of that, if you cool it down with liquid nitrogen, will carry about 2,000 amps, which is about the electricity's worth of like 20 homes. And so we take a bunch of that and stack it into our magnets. And we make a bunch of those. So we take 16 of those. We call them pancakes. Put those together into a case that makes a magnet. These are some of the these are pretty cool things. These are leads that you actually, when you bring normal electricity in and you have to hook it up to the superconductor, you have to have a joint that isolates the heat and allows electricity to pass. So these are those joints. And then this is our test stand where we test our magnets. So we basically put it in a big bucket and then put a lid on it and then pump it down to a vacuum so that the ambient temperature doesn't heat up the magnet. And then we cool the magnet way down inside of a vacuum. And so this is our test stand for the big full magnets. And so we're really excited about what this means and what it can mean going forward for fusion. I do want to touch one more thing just real quickly on the safety piece. Just kind of explain the safety piece one more time. We'll go back to this device. So I mentioned in here that this is where that plasma is. So I said it's going to be really hot, like 150 million degrees, but it's extremely low density. If you think about how much the density changes when you go from water to steam, and if you keep adding energy, that goes from steam to ultimately to a gas and plasma, that gets less and less dense. And so the air outside, that anything that would come into this is about a million times more dense and 150 million degrees colder. And so the fusion conditions immediately quench and you get out of the space where where the plasma can actually create heat. It just stops immediately and turns back into a gas. And that's the kind of the fail-safe nature of it. There's no runaway version of this where there's a meltdown or runaway reaction. There's no chain reaction that's happening. You have to create the conditions where you can have the fusion reaction occur. And as soon as you take those conditions away, it stops and it's the end of it. And so that's really a big part of the inherent safety. And so I moved through that quickly because I wanted to make sure and leave time for questions from the team, because we usually get quite a few questions on what we're doing. And so I think I just hit the 30-minute mark. So I think we're doing pretty good on time. But we'd love to get a chance to answer any questions. I know we have microphones over here on the sides. If anybody wants to step up, we'd ask you to please state your question.
Hey, Ben, Glenn Bester, good to see you again. Question on the regulatory side.
Yeah.
I know you're not regulated by the NRC, so are you having conversations with the Virginia Health Department now with respect to what licensing would be involved?
Yeah, so just to clarify on this, because of this inherent difference in safety, the Nuclear Regulatory Commission in 2022 decided that fusion would be regulated very differently from the way we have to regulate fission plants. Fission plants, you have to regulate the entire design because of what's happened in the past. Whereas with fusion, the decision was really to regulate it more like a cancer research facility or a particle accelerator. In Virginia, you have like the Jefferson Labs, but also all of your hospitals that have cancer fighting measures have some sort of a particle accelerator in there. And so the risk profile by the NRC decided was very similar to that. And so the regulatory framework looks like that. With that becomes the opportunity for a program called the Agreement State Program, where states can actually provide the regulatory licensing for these types of machines. In fact, we've received our license in Massachusetts for the Spark machine already from the Mass Radiological Control Board, which is the same role that's played by the Department of Health here in Virginia. And so we've had initial outreach, but we're still a little bit ahead of where we need to start actually working on licensing for. So we got a little ways to go before we're ready to do that. But as far as like just maybe thinking about that for timelines, we are doing Spark now. Spark will get its first plasma in 26. And then in 27 is when we actually hope to get Q greater than 1. And then after that's when we'll really start trying to accelerate the work on the ARC project here in Virginia. But thank you. Yeah.
Hello.
Hi.
Hi. My name is Lauren. I'm a reporter with the Bay Journal. So I was really curious. I understand plasma is still very volatile and kind of hard to control. At least that's what some of the scientists said at the Oak Ridge National Lab. So I was curious how y'all plan to address that and kind of contain it a bit more, and then how do you plan that the walls don't deteriorate over time, or if you plan to replace that a lot?
Yeah, thank you so much. So just got to repeat the question about the instability of plasma and what it means. And so the plasma, again, is moving around in a circle in here, and we keep that confined by these big magnets. And so the reason you can make it 150 million degrees is because it doesn't touch anything. If it touches anything, it immediately cools off. And so there is something called a plasma disruption, which is very well understood. It happens inside of tokamaks, where a little bit will leak out of the magnetic fields occasionally. So, and then if it touches the wall, then that wall will then obviously be much, much colder and immediately stop that reaction for a little bit. And so that it is an understood and somewhat expected condition, and we design a certain amount of that to be available to the machine. But because of our magnets, we're actually able to make much, much denser plasmas. And we expect the much denser plasmas to have much lower probabilities of disruptions. And so another element, another advantage from having really, really strong magnets is that plasma is actually squeezed that much tighter and is that much denser. And so a lower chance of disruptions inside of our machines than the lower field magnets. I think it's been said once before that holding a plasma with magnets was similar to trying to hold Jell-O with twine. But we've made a lot of advancements in the twine business. So that's a big part of it, is that ability to hold that in place. And then it's within the design specifications that disruptions can occur. And so we'll continue to work on that. There's a lot of work right now on trying to use machine learning to look at plasma performance to try to anticipate. And there's a lot of things you can do to mitigate and disrupt potential disruptions. And so it's going to be a continuing advance of science that's going to happen with the Spark machine that will continuously inform what happens in the first future commercial plants. But I think under those circumstances, a disruption and an increase to safety or risk to safety, that a plasma disruption can happen and there's no change in the safety profile for the machine. It's still safe.
Thank you. I'm Astrika Adams. I'm an attorney with the environmental law firm Beveridge and Diamond. One of your slides said that the expected net energy output would be 10 times the input. I'm assuming that's a continuous net energy output, and I wanted to know what the current data is showing about that figure, including any duration. Is that continuous or some other time frame?
Yeah, so good question. Currently, the only machine that's made more power out than in is the National Ignition Facility in California. It's a research laser, big Death Star of a thing, pointed at a little target. Very much an experiment, not really intended to be any type of commercial power plant, nor does it really have a pathway for commercial operations. So that was the first time, and that was just a few years ago, we demonstrated that. And so when we talk about getting 10 times more power out, then that'll be on the Spark machine. And the Spark machine, because it doesn't have the heat removal process, It has a lot of the systems, but because we're not taking that heat off continuously and turning it into steam and making power with it, it will run continuously. But that one will run for about 30 seconds at a time. 30 seconds is a long time for a plasma. Plasma are very stable in under a second. And then so you don't gain anything for running it any longer. And then the commercial project ARC will actually run for somewhere between 15 and 20 minutes at a time, and then with a few seconds off in between. And that's already been demonstrated by several tokamaks now in France. I think one in Japan recently, maybe China, I can't remember, has done that. So,
Thank you. If I can ask a follow-up question.
Sure.
If you could educate me about the cooling system, is it a closed-loop system, and what is the water demand for the structure?
yeah, so we're going to use an air-cooled condenser system. So we'll basically keep a closed loop to reduce the amount of water that we'll need for the system. Don't have the exact number on hand for what we're going to expect for ARC. I can follow up with you afterwards if you want me to get that for you. But it's going to be intended to minimize that. So we'll use big fans to blow, basically cool off water. So we won't be taking river water out of the James or anything like that. No evaporative coolers that consume a lot of water. So the intent would be we'll sacrifice a few percentage of total power output, but rather than use a lot of water, that's the trade-off. And so we'll avoid that water usage.
Yeah, but that's the weird moment cost. Sterile.
Yeah, so the question was if we have an estimate on how much energy is going to cost when we get to scale. So we look at, actually really excited about fusion by having what we think is a really appropriate regulatory pathway. And it's really about, can we start driving down the cost of the materials? And a lot of the materials were like those superconducting magnets, the superconducting tape. We know and have grown that industry already like 40 times from when we started. And so we can see how much the cost is coming down every time we double the production. And so we're really optimistic about a future. We think about the value of fusion being the fact that it's a clean, firm energy resource, and that we think this will be the cheapest form of clean, firm power available. So if you want to fully decarbonize, that can be a big part of it. And so we think, getting down somewhere in that $60, $70 range in the nth of a kind plants is very achievable. And at that prices, we would be very competitive with every other form of firm, clean power. Solar and wind will be inherently cheaper, but if you think about the balance of those two things, you need both of them to be able to get to the lowest cost total system. And then that can, by having a clean form of power like fusion, you can bring down the total system cost considerably, up to like 62%, some of the math has said, if you can bring that together.
Yeah. When you did.
Yeah, we think it's going to be somewhere in the order. So the question was, how many people do we think it's going to take to run this machine? So somewhere between 150 and 200 people that'll be working at the factory, or not the factory, the machine itself. And then there will be other support jobs. And beyond that, there'll be skilled trades. So there'll be motor rewind shops and things like that have to do things for us that other power plants use for infrastructure. But do see some knock-on effect for other jobs in addition to that. But the core product itself in there is about 150, 200 people for the plant. No, actually, we have a metric on how many physicists, how many PhDs it take to run a fusion plant. We want it less than one. So that's a big part of it. We actually see this being very much the trades of like electricians, mechanics, INC technicians. The things that are working on coal plants today should be able to come and run a steam plant on a fusion device. It should be very, very similar. The actual device itself and how it operates will be able to be managed by procedures, and the way that we train operators today to operate other machines, we should expect to be able to transition the same type of workforce over. So it should be a good opportunity for a lot of different people. We use different trades right now from all over to make these things happen. There's no real exactly a fusion person in the world, minus a few. So yeah, there's a few PhDs if possible. Yeah.
4,000.
So we think about modularity and the ability to scale this. These are our ambitions are to be able to be a company that can make thousands of these. And so if we wanted to make 1,000 of these in a year, we would have to make a magnet, just one magnet, at the same pace that a current Tesla Gigafactory makes an entire car. There's one factory. And so like all of the, like we did 1,000 power plants would power the United States pretty comfortably, or its transition. So being able to do that is kind of the idea that this could be a very repeatable process. We need about the same amount of steel as like a Hyundai heavy shipyard would need in a year to make oil tankers to carry oil back and forth across the ocean, which we would probably need as much anymore. And then we'd have to make that superconducting tape at about the same rate that like a thin film solar manufacturer puts together thin film solar panels. Need about 3 or 4 of those for global capacity to reach 1,000 power plants. So we think there's very much the capacity to grow and build this business to grow and scale a lot of power plants. Yeah.
So mention is with way. You mentioned you talking about what side is this that a sacrifice here that renting whatever to I to back or other is the way but that makes it but especially then and some of whether or not about.
Yeah, it's a great question. The question was around primarily, do we have the concerns about resources that we need to be able to scale up and build the machines? And so there are some things that would need to be expanded in order for production. But we have the means now to get the first ones built, and then we then put demand signals into the world for those to happen. And the resources exist. It's just maybe that the extraction or the refinement of them to our quality hasn't been scaled up yet. So those will have to scale with us as we go forward. An example is beryllium. We use that in our molten salt. Beryllium is in a mine in Utah. There's a lot of it in Utah. That mine is relatively underused right now. And so there's more capacity there with the installed to get more of that metal out. But that is not expected to be a limiting condition, but it's an example of something that will scale with us as we go. Yeah.
Hey, I'm good. I call it. Well,
Yeah, so like it comes back to this idea that the heat is really contained by the magnets, so it doesn't touch anything. So the rest of it doesn't get super hot. 600 degrees is hot by other terms, but that isn't actually a liquid molten salt that is designed to melt and get hot, and that's the heat transfer system. And so this part is replaceable, and so over time this will wear out. In about every year or two we have to replace that part, but the rest of it should last between 20 and 30 years, from as a power plant, and designed such that this part, which is now becomes kind of sacrificial because it's going to see all of that heat and potential, the neutrons are going to hit it and pass through it, and over time this will need to get replaced, and that's designed to be replaceable. And so what other fusion machines have done before us is they had all this be a very big, strong, tough structure that needed to last 20 years. So it had to be really, really big and really, really thick. By putting this molten salt around the outside of it and keeping this as a modular product, then we can allow ourselves a lot more flexibility for operations. Yeah. So the great question, the question was like, will it be bursted energy or consistent energy? So while the machine operates somewhat in a pulse fashion, this molten salt stays molten the entire time. And so the steam production is consistent throughout the whole time. If you're constantly making electricity, you don't see a fluctuation. So the transmission grid will just see 400 megawatts of output. It will look to the grid like a natural gas plant, and they won't see anything different. So yeah, absolutely integrates seamlessly with the existing grid infrastructure. Yes, sir.
What last name? What do you do? I think it's like
Yeah, we searched for almost 2 years looking around. So the confluence of a number of factors. We liked the environment of where Virginia sits just geographically, in the proximity to be able to show people what's happening and have accessibility to it, to be able to get our people from Massachusetts down to the project with ease was another contributing factor. We needed fundamental infrastructure. So we need to be close to power lines. We needed to have a site that was appropriate for a power plant that would work in a power plant siting. We also were very thoughtful about who and what the workforce and talent looked like in the region, what the capabilities of that workforce were. And so we continued to look, we really got more and more excited about Virginia. And then as we've gone through that, we've now made really strong partnerships through Virginia. from both the state, the county, and also with the Dominion, the local utility, which you have to work with if you're going to build a power plant. All of that together has just continued to fortify that this was the right place for us to come for our first project. Yeah.
Like the past of the
Yeah, so the question was like, how has environmental concerns informed the design? Like that. Yeah, okay. I think like one example is pretty straightforward is that tritium is a milder radioactive form of hydrogen. It sometimes shows up in fission plants. Fission plants made the mistake often of burying their pipes that had tritium in them, and they buried them in places that were inaccessible and couldn't do inspections. And so that was an obvious lesson learned. It says, don't bury any of these pipes, make them inspectable, make them variable so you can detect anything. And so that's an example where we applied operating experience to how we think about the design. And overall, I think the iteration of this is from building on all the experience of previous plants, that it is still fundamentally inherently a safe product. Then we also lay over like industrial safety type things. And so we have a radiation safety officer and a program designed to make sure that our workers are safe and that the environment is maintained safe at all times through that process.
Here's that battery.
Yeah.
it's that needs 80 drugs here down. Go lights. Let's do go.
Yeah, so electromagnetic fields are a thing. So it's called a non-ionizing radiation is a magnetic field. It will not be felt outside of the machine here. So it actually drops off very quickly. So it doesn't propagate for long distances. So it's stays very tight, and so it drops off at the square of the radius. So we can keep it very much contained in here. It is something we have to be mindful of. We don't, like when we're testing our magnets, if you have a pacemaker, you can't. So we have to make sure that we're doing those types of things. Because the magnetic fields are real. They are strong, but they are not a threat to the environment.
One last question asked here. Yeah, around years, right? Oh, but so, oh wow.
So no intent to use natural gas. We are pulling it out of the air. I don't know exactly what the final design is. Sorry, I have to follow up on that. But we will just be using liquid nitrogen. So we'll take it out of the air, compress it, and turn it into a liquid, and then we'll basically evaporate it back out and to cool off the helium that we use to cool the magnets at the first stage of cooling. I can look up the other question for you, but no intent to use natural gas for that process. Okay. Thank you all for your questions. Very much.